vertex separator problem, I will show you some of our recent results that we have published in the journal Operations Research. So the whole talk is based on this paper, which is a joint work with my colleagues, Fabio Furini, who is professor at La Sapienza in Rome, Enrico Malaguti, who is professor in Bologna, and at the time when we were working on this problem, Paolo Paramuzzi, he was a PhD student, now he's also assistant professor in Bologna. So actually we are not going to study one problem, but two. And the first one is very intuitive, and you can think very realistically about applications of this problem, because it's somehow related to immunization of social or communication networks. So the problem is as follows. In a given graph, which can represent communication or social network, we want to find a subset of nodes that we will call it S. We can also refer to this as a separator set that we want to remove from the network. And what we want to achieve is that this subset of nodes guarantees that after the removal, the size of the connected component in the remaining graph is the smallest possible. So we bound the cardinality of this set to B, which could be our budget. And now you can think of this application as immunization against the propagation of a virus in the network. So these vertices that we are removing could be the vertices that are immunized by the vaccine, or if we talk about possible cyber attacks, where the virus would, the computer virus would be spreading through the network, those would be the nodes that you will have to turn off from the network, or where you will have to install some special security measures. And then you will be sure by finding these nodes and by finding the largest connected component, you will know exactly how many nodes would be affected by the viral attack in case that this virus appears anywhere in the network. So as an example, here we have this example here. If we are allowed to protect only 2 nodes, then in this network, the largest connected component that remains will have the size of 24. However, if we can protect 4 nodes, then the largest connected component that remains after protecting these nodes or after removing them will be of size only 10. Okay, so the same, another interesting application would be also in the spread of the fake news. And then you would say, okay, these nodes that you are protecting are the ones that will block the spread of the fake news, because the news will be spread no matter where they appear in the network, only inside of their connected component. So the problem has been introduced back in 2000, where the authors have shown and called it that by protecting a relatively small number of vertices, which means by removing them, we could actually achieve significant improvements in protecting our networks. In other words, the size of the largest connected component, and especially in the scale-free graphs, goes down very fast by just slightly increasing the number of nodes that we have to protect. In terms of methodology, what the authors proposed in this paper in 2000 was actually a simple greedy heuristic. So they said, okay, let us sort the vertices based on their degree, and let's remove one by one those with the highest degree until we reach the budget B. Okay? However, this is clear that this greedy heuristic doesn't provide the optimal results, and relatively late, so 12 years later, the people from the OR community studied this problem, and it was Sikian Shen and co-authors, including Cole Smith, and they provided the first exact ILP-based formulation. And besides that, they also showed that this greedy heuristic actually can provide arbitrarily worse results, which means it can be arbitrarily far away from the optimal solution. They also studied the problem in the trees. Their model was an extended MIP model, which means it did not use just the natural variables, where the natural variables that would be sufficient to describe the problem would be just the 0, 1 variables telling whom do we want to remove from the network. They had an extended space, but it was a nice compact formulation. So this is the first problem that we will be addressing. So it's called minimize the maximum component in a graph by removing a subset of vertices of a given cardinality. Another problem is similar, but the definition is a little bit more complex. So it's called the capacitated vertex separator problem. So these vertices that we are removing, they are called the vertex separators. But now we have an additional parameter. So now we have two integer values, k and b. And the goal is to find the smallest subset of vertices, as, again, this separator, to remove from the graph. Now, what do we want to achieve? Now, when we remove these vertices, the graph will fall apart into many connected components. What we now want is that we take these connected components and to pack them into k bins, like a bin packing problem. And capacity of each bin is given by this number b. So for example, now what we minimize is the number of nodes that we need to vaccinate, to immunize. So for example, if we are given only 2 bins and each of the capacity is 17, then we will need in this example at least to immunize 4 nodes so that we will be able to pack this component into 1 bin. And then here you see we have several components. We have isolated vertices plus this connected component. We put them all together in the second bin of capacity 17. Also here, if we are given 4 bins and each of capacity 9, then you can see we only need 1 more vertex and we will be still able to pack them. So the color code here represents 1 bin with the packing. So we have this component plus isolated vertex and so on. So the bins, I will sometimes refer to them as shorts. They are given the size b, which is the input parameter. We are given the number of bins, and what we want to find is the subset of vertices to remove of minimum cardinality. Now, applications of this problem are completely different, and they come actually from the applications in parallel computing. And in particular, if we are given, for example, linear programs of a very large size, what we would like to do is to decompose these linear programs into bordered block diagonal form by removing some of the rows. And removing means relaxing them, for example, in a Lagrangian fashion, so that we obtain block diagonal matrices. And so that then each of these blocks can be scheduled on one of the k given parallel machines. Okay? So in other words, what we are doing is we are given a linear program, and for each row of the matrix, we create 1 vertex. Then we look at the columns, and if in 1 column, 2 rows have the non-zero entries, then we connect these rows by an edge. Okay? And finally, now removing these nodes means removing the rows from the matrix. After that, we obtain 1 block in the matrix, another block in the matrix, and so on. And then each of these blocks will be scheduled on 1 machine, and there will be k machines. And now what is the role of this parameter b? Well, we want that the workload on each of these machines is somehow balanced, and that's why we limit the size of each of these blocks. So this is the idea. This problem has been introduced in 1998, and for this problem, Bardorfer and colleagues from Berlin, they have developed a quite sophisticated branch and cut algorithm, again based on an extended formulation. Again, not in the canonical space of variables, because also for this problem, it will be sufficient just to work on the binary variable saying which are the rows that we want to remove from the matrix. And then very recently, a branch and price algorithm has been developed by Marco Lübeck and his colleague Bas Stube. And they worked on the problem on hypergraphs. Okay, so so far so clear. So I hope the definitions of the problems are clear, and please do not hesitate to interrupt me in case you have any questions. Okay. So let's start with a standard mixed integer programming model for solving this problem, capacitated vertex separator problem. They are similar. I will show you in a few slides later where the connection between the two comes from. And because this one is more general, we will talk about the CVSP in the rest of the talk. So we will start with this extended formulation, which is of polynomial size. So we say it's a compact model, where we have binary variables, psi I v, which will be equal to 1 if the vertex v is assigned to a shore I. So shore or a bin, okay? So if the vertex is assigned to a bin, then a bin with index I, then its variable will be, binary variable will be set to 1. Now, the vertices that cannot be assigned to any bin are the ones that have to be removed, are the ones that will belong to the separator S. So by maximizing the number of vertices that we can assign to one of the k bins,
I think we're still here, but we've lost the speaker.
Yeah, I think we lost you, Werner.
there is no distinction between different bins. This means that the same solution can be obtained just by looking at a different permutation of the indices of the bin, which is a real nightmare for branch and bound based approaches, because then we cannot move up the bounds, the dual bounds. And the second problem is the size of the model, because it contains the number of bins times the number of vertices of variables. So even though the constraints 1c could be slightly improved by replacing the edges with clicks in these constraints so that we are sure that we cover all the edges, still we would not be able to significantly improve the performance of this model. So there is another alternative way, and as I said, that would be a basic canonical formulation of the problem, in which we would like to work in a sparse set of variables, which means why don't we try to develop a model in which it will be sufficient to decide only who will be the vertices that belong to the separator, and then we will work with an exponential number of constraints, which will lead to a branch and cut approach for this problem. And indeed, this model, this bare bone model, has been proposed originally in 1998 by Bordorfer and colleagues, but they did not provide any computational experiments for this one so far. So what we have here is the following. So in the objective function, we minimize the size of the separator. Let's start now with constraints 1c. In 1c, we say the following. If c is a connected component of the input graph with the number of vertices, which is b plus 1, then we know that we have to remove at least one of the vertices from this component, right? So now the second constraint, 1b, is a little bit more complicated. So what is this sigma of w? So w is subset of vertices. And sigma of w is a function that calculates into how many bins of size b we can pack all the connected components induced by this set of vertices. And if this number is larger than k, this means that in this subset w, again, we have to remove at least one node. And so this is the constraint which can be separated only by solving the underlying bin packing problem. So clearly, separating these cuts is anti-hard, but we cannot avoid it because this is in the nature of the problem, right? So we need each bean to be of size B, and we need to work with K beans. Okay, good. So now what our goal was, so we call these bean packing inequalities, we will keep them in our model. And our goal was now to start with this model and to enhance it with additional families of valid inequalities so that we can make this model computationally, let's say, useful for some of the benchmark instances that are known in the literature, for some of the instances that might be of realistic size, at least when it comes to the decomposition of LP problems. And so for that purpose, we now looked into the problem from the bilevel perspective. So this is the contribution of our work. We start with this canonical MIP formulation and then provide two separate ways of looking into this problem as a Stackelberg game. And we use the tools of bilevel optimization, and I will give you just a short introduction into what it is, in order to derive three new families of cuts. And we call them Bender's cuts. Actually, Bender's cuts, they come also from the LP duality theory, but component cuts and the degree cuts, they come from the real bilevel structure of the problem. So then we integrate these cuts into a branch and cut framework, and what we managed to achieve is to beat the state-of-the-art results for these two problems, for both min-max component and for the capacitated vertex separator cut problem. Okay, so Stackelberg games, they are known in the economics. They have been introduced back in the 30s by Heinrich von Stackelberg, and they represent sequential two-player games, in which we have the first player, to which we refer as the leader, and the second player, to which we refer as the follower. So now, what are the rules of the game? The follower, the leader moves first, the leader makes a decision, and then the follower observes this decision and then tries to maximize her payoff. The key point is that the leader can anticipate the decisions of the follower because the leader has the perfect knowledge of the strategies of the follower, which means that the leader can integrate into his or her decision-making the answer, the optimal response of the follower. So both of the players will maximize their payoffs and they will act rationally. So here is a simple illustration for combinatorial optimization problems. And so the leader, in our case, would make a decision about the separators, right? So the leader wants to decide who are the vertices to be removed from the network. And because it's a combinatorial optimization problem, we will have finitely many choices to choose between the separator S1 and so on up to the separator Sn. After the leader removes these vertices, then the follower observes that these vertices are, we can also say, interdicted from the network, and then the follower solves some combinatorial optimization problem in which the follower maximizes her payoff. Because the leader knows what is the optimization problem of the follower, the leader can now anticipate the answer. If the leader says, okay, if I interdict vertices S1, the follower will respond with T1. And so now I can pre-calculate my payoff for this decision. Okay? If the leader says, if I interdict the vertices Sn, then I can anticipate what will be the answer of the follower, what will be the optimal solution of the follower in this case. And so then I can go back and calculate my payoff for this decision. And so among all these choices, now the leader takes the optimal one. So that would be a kind of a double exponential full enumeration. And it's clear that in practice, we will never do something like that. And our approach would be to instead develop a branch and cut algorithm that will mimic this process. Okay. Okay, so in terms of mathematical optimization, this is the way how we can model Stackelberg games. So we have two types of decision-making variables. They are X, and these are the variables which are controlled by the leader, and Y are the variables that come as the optimal solutions of a nested optimization problem of what we call a lower level problem, which is a parametric optimization problem which depends on the decision X of the leader. So for any choice, any fixed decision X, in the lower level, we are solving this optimization problem, and Y is an optimal solution of this optimization problem that then becomes part of the leader's optimization problem. In our case, we will work with a special kind of the so-called linking constraints, which we will refer to interdiction-like problems. Because in our case, all these connections between the decisions of the leader and the follower in the lower level, they will be given by these type of inequalities. Remember, V is a vertex of the graph, and X will be our decision whether we are interdicting the node, the vertex the leader is interdicting the vertex, removing it. And in that case, we will say, okay, this vertex will not be available for the follower. So in this general definition, just to mention these bilevel optimization problems, functions f and g could be arbitrarily functions. They could be convex or non-convex. They could be linear, and also the sets. X, we could also introduce additional constraints here, imposing that, for example, variables X and Y are discrete variables. And so we will end up with different families of bilevel optimization problems. In any case, there is a nice trick for reformulating these problems using what we call the value function reformulation of the bilevel optimization problem. So what we see here is we actually request Y to be the optimal solution for the lower level payoff for the objective function of the lower level problem. And we can state this in a different way. We can say that the value of the lower level problem for given any X and Y has to be less or equal than phi of X, where phi of X is the optimal solution value for the lower level problem whenever we fix the value of X. So phi of X is a function that describes how the value of this optimization problem changes while changing the value of X. So this is just another way of restating this bilevel optimization problem, but it will be very helpful or very useful for us in the following, because we will use this value function reformulation in order to state the desired properties and in order to derive new valid inequalities for the problem. Okay, so there is also another important notion of for bilevel optimization problems. We can, in this definition, actually, we need to distinguish between optimistic and pessimistic bilevel optimization settings. If we simply assume that the leader, if there are multiple optimal solutions of this lower level problem, so whenever we are given X, there are multiple Y's that could be taken, then maybe for some of these Y's, the value of the objective function of the leader is better or worse. In the optimistic setting, we will assume that the leader can choose among multiple optimal solutions the one that works best for him or her, right? So it will choose the most optimistic response of the follower. And in the pessimistic setting, we will say, on the contrary, the solution that is returned by the follower is the worst one with respect to the objective function of the leader. In our case, we will work with the optimistic setting, okay? And actually, one can show that for this specific interdiction-like problems that we have, there will be no distinction between optimistic and pessimistic, but I'm not going into these details in the rest of my talk. So let's see now, how can we see this capacitated vertex separator problem as a Stackelberg game? So the first way is the following. We will simply state this property as a bilevel optimization problem. We say that on the interdicted graph, which is the graph after we have decided which vertices to remove, so we remove them, so we call this interdicted graph, the size of the largest connected component cannot be larger than B. This is simply because the capacity of each bin is given by B. And in that case, we can now define the follower subproblem, the lower level problem, which is now like the leader has removed the vertices. Now the follower looks into this network, and what is the optimization problem that the follower is solving? The follower now searches for the largest connected component in this interdicted graph. And this is the value function constraint that now we have to impose. We will say phi of x must be less or equal than b, where phi of x models the size of the largest connected component in the graph in which the vertices whose xv is equal to 1 are removed. Okay? And by doing this, I will show you that by the bilevel reformulation, we can derive the cuts that we refer to as component cuts, but also using the LP duality theory, we can actually also derive Bender's cuts that will guarantee the same property. So this is the first way to see it as a game, and that will give us some valid inequalities, these two types. Another way would be the following. So first of all, so the functions phi of x, these value functions, for most of the interesting problems, are highly non-convex and very often non-continuous. So the major trick when solving bilevel optimization problems is to find a way to convexify this value function. And in Bender's cuts, this convexification is simply guaranteed by the LP duality, whereas with the component cuts, I will show you the technique that I refer to as convexification by penalization. Okay, another way to look at this at the game would be the following. We will use this property. If you're given a graph with n vertices, and we would like to know what is the minimum number of components that this graph has to fall apart so that the size of the largest component is bounded by B. And this is just a simple formula that tells you, okay, if I have n vertices, each component cannot be larger than B, then this is just n divided by B. If I'm allowed to remove s vertices from n, then the number of components that this graph has to contain is n minus s divided by b rounded up. So at least that many connected components we must have in the graph of size n from which we remove the s vertices if we want to guarantee that each component is not larger than b. Okay, now we want to translate this property into linear inequality. And we can do that as follows. So these numbers here, and we will look at the connected component with more than b vertices. The number of vertices in the component minus the number of vertices that we are going to remove divided by b. This is the number. Now, what is this function psi of x? Well, this is another lower level optimization problem in which now psi of x calculates the number of connected components in the graph in which we have removed those vertices where xv is equal to 1. So this is another optimization problem to solve. And this now optimization problem simply looks into the graph and counts the number of components in the interdicted graph. So as you can see, so we have two value functions. One is phi of x, where we calculate the largest connected component. The other one is the one where we just count the components. Okay? And now these inequalities here, they have to be translated. The major goal is, again, here we have an issue that these functions, this value function is in general non-convex, non-continuous. So how can we make these constraints become convex constraints or ideally linear constraints? So here I already explained you. And here we will also do the same. We will apply convexification by penalization technique. And of course, we will have to get rid of this rounding because we will just simply remove the rounding and work with slightly weaker constraints. So for the rest of the talk, I will actually focus on the largest connected component, and I will explain these two. And in an analogous way, analogously, convexification by penalization will be applied to these cuts as well. Okay. So what happens with our model actually when we apply the value function reformulation? So here we are with the problem of minimizing the maximum component, maximum connected component in the graph. So we have our x variables, which are binary variables. And now with x in x, we denote all decisions. Remember that we're here given a budget B. So we say we can remove at most B nodes. So this is encoded by this. And we want to minimize the size of the largest component. So we say minimize max of phi of x, because remember phi of x just measures the size of the connected component after removing vertices from x. And we just reformulate it using this epigraphic reformulation by introducing an auxiliary variable w. And now the major goal is to translate these cuts, these inequalities, into linear constraints. So this is how we would be modeling the minimum, maximum, min-max component problem. On the other hand, when we look at the capacitated vertex separator problem, we will end up with a very similar structure, with a very similar type of constraints. What we do now is we minimize the size of the separator. And so x in x are now just simply binary variables. And plus the conditions based on the bin packing inequalities, they are included here. And now, in addition, we enhance this model by enforcing that after removing the vertices from S, the largest connected component cannot be bigger than B. Okay, and so what you see here is that if we would be able to translate these inequalities by convexifying the function phi of x and replacing it with a possibly exponential number of linear constraints, we would end up with two very similar ILP models that could be solved, both of them using branch and cut approach. Okay, so how can we do that? How can we achieve this? So for the component cuts, which I'm going now to introduce first, remember the goal of the follower is, this is the lower level optimization problem, is that once the decision of the leader is given, which is x star, the follower wants to find the largest connected component. We can model this as another integer linear program like this one, for example. So the follower will now look at the decision of the leader, and it will say, okay, I have binary variables 0, 1, and uv will be equal to 1 if the vertex v belongs to the largest connected component of the interdicted graph. So these are the interdiction constraints. They say that if the leader has removed this vertex, then I cannot put it in the largest connected component. And these constraints 1c, they state the following. If the vertices v and w are both in the same connected component, then there must be a path connecting them so that along this path, all the vertices are taken in the component. Okay, so this is a visualization of these cuts. So we say the vertex set F is a node separator for the vertices u and v if any path from u to v has to cross at least one of the other vertices from F. And so these are node separator inequalities saying, okay, in that case, if u and v are both in the connected component, then at least one of the vertices from F must be taken as well. So anyway, what we can do now is the following. We can encode all these constraints that do not depend on the decision of the leader into a set, combinatorial set Y, okay? And then we have these interdiction constraints that are linking the decision of the leader with the decision of the follower. So how can we deal now with this? because it's a binary problem and we cannot relax integrality constraints without loss of generality, we cannot use LP duality here. So what we're going to do is we are going to translate this problem into an equivalent one by penalizing these constraints, these linking constraints, by inserting them into the objective function and multiplying them by the big constant big M. Because actually imposing that YV must be 0 whenever XV is 0 implies that the product of X and Y for this given vertex must be equal to 0. And because we are maximizing the objective function, then for sufficiently large big M's, by penalizing this product, we can ensure that this property will be attained, even though we relax these constraints and solve this optimization problem instead. So it's a kind of a Benders-like decomposition, because now this optimization problem, the feasible space of this optimization problem, is just simply the set combinatorial set Y and does not depend on the choice of X anymore. Which means that now we can equivalently optimize this problem over all feasible points, or because the objective function is linear, over all extreme points of the convex hull of the set Y. Okay? And this number of extreme points is finite. It's probably exponential. And so Y hat is simply just one possible connected component in our input graph. And then we look at the maximum of this objective function over all possible connected components. And now this function phi of X, by restating it in that way, becomes a convex piecewise linear function. And so this is our convexification that we were looking for. Which means that the value function constraint can be now reformulated in this way. And so now the blue Y hat is actually a constant vector, and this represents one connected component. And so what we have here is simply a linear function in X. But we have possibly exponential number of constraints to impose to replace this. Okay. Now, after restating it, this is what we obtain. This is what we call component cuts. Now, of course, we have an issue here with big M. And the question is, we want to find the tightest possible big M's. And how can we do that? So this idea has been originally used in the context of interdiction problems by Wood and colleagues. And there are some theoretical results that we know. For example, for linear programs, Wood has shown that the tightest possible big M's, if the problem that we are solving here, the set Y, is a pure linear program, they can be found by finding the right upper bounds of the reduced costs of these interdiction constraints. Then recently, we looked at the more general integer programs, and we found that if the certain downward monotonicity property is satisfied, then these big M's can be exactly the same as the coefficients next to the Y variables here. We also show that this is true for some special problems where the hereditary property is satisfied, but in general, whenever we apply these penalization techniques, finding the tightest possible value of big M is actually an open question, and in principle can be an NP-hard problem on its own. So what did we do now? How did we find the appropriate big M's in our case? So basically, this is our optimization problem that we are looking at. And it turns out that the big M's here correspond to the largest deterioration of the objective function after removing the vertex V. So if we are given a tree like this, the question would be, okay, this is a connected component of 9 vertices, but if we interdict this vertex, then the objective function deteriorates and the largest connected component has the size of 5 only. And so it turned out that with this reasoning, we can set the values of big M into the size of the component minus the size of the largest connected component that remains after removing the vertex V. And so we got a little bit tighter cuts than by just putting into these cuts just arbitrary big M values. And this is what comes as a formula. And now here, what you can see here is that we are imposing these cuts now for any t from T of C. So what is this notation? So whenever we have a connected component larger than B, so that the large right-hand side is bigger than 1, greater or equal than 1, then we look at an arbitrary spanning tree of this component. In this spanning tree, we remove the vertex, we find the largest component, and these are now the coefficients of our cut. So clearly, the separation of these cuts can be done in polynomial time whenever the solution x is integer, and it's based on the breadth first search. So that was the first way to derive cuts, and we call them component cuts, by interpreting the problem as a bilevel optimization problem. The other way is by using the LP duality theory, actually, and that way we can derive Bender's cuts. Now, when we look, we could also alternatively look into the followers problem and model it as a minimization problem. Okay, this minimization problem is now a pure linear program. Okay, because it's clear that when we remove the vertices from the graph, searching for the largest connected component is a polynomial problem. So it is clear that there exists an LP formulation that can model this polynomial optimization problem. And this formulation is given here. So this formulation comes from the paper of Shen and colleagues from 2012. And what do we have here? Now we have again the vertices which are interdicted, and the variable lambda is now modeling the size of the largest connected component. The variable sigma VL is equal to 1 if the vertex L and the vertex V belong to the same connected component. And so lambda is greater or equal than the size of a component in which the vertex L is taking part of. And so by stating this for all L, lambda will be the largest connected component. And constraints 1c, they simply state that the vertices V and W cannot be in the same component if either W or V is interdicted. Okay? And it's a pure linear program. So now what we can do is we can apply the LP duality to this linear program. After dualizing this problem, then this dependence on the leader variables goes into the objective function. And again, then we have the dual of the LP, which does not depend on X anymore. And then again, I'm skipping all this theory of Bender's cuts by enumerating all possible dual extreme points of the dual of this problem that do not depend on X. We end up again with a piecewise linear description of this optimization problem. And so we can again replace our cuts, phi of X less or equal than B, with a different type of constraints, where now these coefficients come from the dual, are defined by the extreme points of the dual of this LP. Okay? Good. So it turns out that whenever X is binary, we do not have to solve the dual of this LP in order to be able to derive these coefficients, as this is the standard way when we are deriving Bender's cuts, but instead we provide a combinatorial optimization algorithm that is based on the breadth first search again, that will calculate these coefficients. Okay, and so here we are again. So this is the way how, by looking into the largest connected component, we were able to derive two different types of cuts. And as I said, the similar way for the convexification by penalization would lead to what we refer as degree cuts. Okay. For the degree cuts, just one slight remark. We were using this very well-known property from graph theory, because remember that the function psi of C simply counts the number of connected components. And so in a graph G has at least Q non-empty connected components if and only if, let's say, any spanning forest in this graph contains at most V minus Q edges. Here is an example. If you have a graph with 9 vertices and the graph contains 3 connected components, then the largest number of edges of any spanning forest in this graph will be 9 minus 3. Okay, and here they are, for example, shown in red. So by using this property, then we model this function psi c as an integer program in which we maximize the edges that we can put into a spanning forest after interdicting some of the vertices in the graph. Then we apply the convexification by penalization, and this is what we get as the final cuts. Okay, to sum up, again, also separation of these cuts can be done based on the breadth first search. So here are these 3 different families of cuts, and what you can observe is that the right-hand side is always the same. It tells, we always derive these cuts on an arbitrary spanning tree from the given connected component. And what differs here are the coefficients. So the first thing that we can do is we can tighten these cuts, because whenever the coefficient here is larger than the right-hand side, we will round it to the right-hand side. And after doing that, we were able to show that actually Bender's cuts are dominated by the component cuts, and that there is no relationship between component and degree cuts, which means that they could be useful in theory. It would be useful to separate both of them in our models. Okay, so now we can move to computational results, but I can have a short break here. Maybe you have some questions regarding the derivation of the constraints so far. You may also wish to type the questions in the chat. If not, then let's move to computations. So in the computational study, we tested almost 1,400 instances that were available from the previous literature, and they are quite diverse. So instances representing matrices of LPs from the netlib library with up to 500 vertices. Then the graph coloring instances from the Dymax library, we also with up to 500 vertices. Then pre-solved MIPS from the MIPLib, and randomly generated graphs that were recently constructed by Marco Lübecke and colleagues. Then, when it comes to the size, to the number of bins, we consider 3 classes of instances with small number of bins, medium, and large number of bins. And the capacity of each bin was, as proposed in the literature, set to this value. We had a half an hour time limit, single thread runs, and the first results that I want to show you here are representing the results of 4 different branch and cut algorithms. So remember that we always have to separate the bin packing inequalities, and on top of that, then we separate here component cuts, degree cuts, Bender cuts only. And we also tested many other variants. I'm just showing you here the winners. And the winner was the component cuts plus cover inequalities that I didn't have time to show you, that were cover cuts earlier introduced in '98 that basically exploit also the fact whether the connected component is biconnected. So what we see here is the results are disaggregated by small, medium, and large instances. When we look at the total results, the component cuts are able to solve 925 instances to optimality, which is the largest one of each individual contribution of these cuts compared to the degree or to Bender's cuts. But the best performing one are the cuts with the cover inequalities, where we managed to solve 940 instances in total. The average time that we report here refers to the time for those which are only solved to optimality, not overall. And the same is true for the average number of branching nodes. So why do we have such a large number of branching nodes? This is because we did not separate fractional points in our preliminary experiments. It turned out that it just slows down the branch and cut procedure. So we take advantage here of the branching strategies of CPLEX as well. Okay, and then when we look at the performance profiles, and here I'm showing you distinction, or let's say differentiation based on the value of the number of bins. When we have large number of bins, then we are comparing here our best performing method, branch and cut, against the branch and price, and against CPLEX. And CPLEX is here. So what you can see is that the performance of black box solvers on this compact formulation that I have shown you at the very beginning is really bad. And this can be here explained by the fact that we have a large number of bins, so up to 256. And this way, when you multiply it with 500 of vertices, first of all, you get a huge ILP. And second, then clearly the issues with the symmetries are enormous. On the other hand, if we have a relatively small number of bins, what you can see here is that the black box CPLEX solver actually is able to outperform us on a small set of instances. And K small then really means like K equal 4, 8, or 12. Okay? Here, when you look at the differentiation based on the type of the graphs that we were looking at, you can see that our method is outperforming all the others everywhere except for the randomly generated graphs where the branch and price is better. Okay, so what about the min-max component problem? So in the min-max component problem, we don't have these degree constraints. We work only with the component cuts. And here again, we are comparing two compact models, the one with psi variables, the symmetric one, then the one with lambda variables that I was showing you where we were deriving Bender's cuts, proposed in 2012, and our model with component cuts. And here again, if we look into the total, now we have 564 instances. Again, the winner is the branch and cut with component cuts. And also when you look at the average time, it really goes significantly down compared to the other two methods. So to conclude, what are the takeaway messages? First, I would like to generalize now these ideas is as follows. So in many problems that where we want to protect critical infrastructure, we are looking into some centrality properties of the nodes or the edges. And very often in the computer science literature, the authors are looking into some kind of node centrality, which is based on the individual node centrality. So like what we saw before. So you could say the most influential nodes are those with the highest degree, with the highest betweenness, distance centrality, eigenvalue centrality. You can come up with many, many different criteria. The point is that these nodes may have individually a big influence on certain structural properties, but as a collective, they may be outperformed by another subset of nodes where individually they are not so much important. So for example, here, if this size of the nodes corresponds to their individual node centrality, whatever it is, one of these criteria, for example, if you would in a greedy way remove, let's say, the 4 largest ones, and you want to destroy the network in the sense of destroying some connectivity measure, that might be much worse than maybe removing these one and then some of the smaller ones. In other words, we have to look at the global perspective, and we have to look at the collective centrality of nodes instead of individual centrality. And this is what we do with these vertex separators, because we look at an optimization problem and we say collectively, we look at the impact of collectively removing a subset of nodes from the network. What will be the impact to the connectivity of this network? So this is one way where we need to better exploit and understand these problems. So rather than just removing the vertices, sorting them based on some simple criteria, removing them in a greedy fashion, it is always recommendable to solve the underlying optimization problems. On the other hand, for example, what are these connectivity-based centrality measures? So the min-max component problem obviously says the functionality of the network depends on the size of the largest component. But maybe in some other context, you want to say that functionality of network is actually related to the number of connected components or to the number of pairwise disconnected pairs. If it's a communication network, you want to measure what happens after destroying the network, how many nodes can pairwise still communicate with each other, or if we have like some kind of social network, we may measure the connectivity as the size of the remaining largest clique, and so on. So there are many problems that, that we still can solve using this idea of looking into the problems as a two-player game. So the first player is the one that looks at the collective subset of nodes to remove or to protect from the network. And the lower level problem is the one where we are optimizing some of these connectivity measures. And this is true not only for the deletion of the nodes, but sometimes we want to enhance the networks and we want to look into node insertion problems. So for example, then the question is, how many nodes we have to insert into the network? How can we improve the infrastructure so that we improve some of the connectivity properties? And so I invite you to explore this bi-level perspective of these problems in any of these, if you find it relevant for your applications. So indeed, and again, as a takeaway from this talk, it is true that in principle, bi-level optimization is very difficult. It is true that if you have a bi-level optimization problem in which the upper level and the lower level are simple linear programs, the problems are already NP-hard. But many problems from graph theory, when these lower level problems are especially linear programs or polynomial, can be efficiently approached from this perspective. And in particular, they can help us to develop these, what I call FIN models, which are canonical formulations in which you don't have to work into the extended space of variables, you work in the natural space of decision variables. What are interesting for the future directions for future work? Well, how can we exploit these ideas, for example, when the follower subproblems are nonlinear, but hopefully convex? What if the follower problems are submodular? Or what if we have to involve uncertainty? And the uncertainty can be at the upper level, at the lower level. We can have now, because we have two players, we have different stages where the uncertainty can be revealed. It can be revealed for the follower before making the decision or after making the decision. And so there is really this really rich field of possible research questions. And then we have three-level games. So I'm giving you just a few references of some related work that I've been working on in the last few years.